All right. Okay, awesome. Let's see. Actually, let me get this off. I might. Topologically challenged. All right. Okay, now to something completely different. Actually, what I want to share with you is just a few papers that we wrote the last couple of years in the context of analyzing logical structure data to describe clustering. I think as we're all aware of, like when people talk about clustering of galaxies, clustering of anything, usually what's implied is they're talking about the two-point correlation function. And so what we're trying to do, mostly with my collaborator Arka Banerjee, who just became an assistant professor in Pune in India, and a number of students at Stanford, Richie Wang, Al Samora, worked with Risa Wexler and I, postdocs at Nijuan, and also Nick Cochran. I'll give you a few examples of what these new statistics are useful for. And yeah, and just hope, it gives you, that you might be interested in, it becomes another tool in your tool belt if you want to analyze spatial clustering. So the minimal problem that we're sort of thinking about is we've got a list of points in 2D, 3D. Actually, it's really dimension independent, but you just have a list of points in your space, and maybe that's sort of a funny window function or is a funny selection thing. So that's definitely something you want to keep in mind. And you now want to somehow describe of what is that pattern, what is that spatial pattern of these points. And what was really, what's sort of fun for me to learn about the statistics generally is like, there's sort of any operation that operates on all of these points together and averages them in some way or multiplies them or any of that would be a statistic, right? So the world's your oyster. You could choose really anything. So you have to think, okay, what's my design goal? What do I want to get out of the procedure that I'm going to invent? Otherwise, I could just take the mean or the median or, anything. And so that's a little bit some of the metrics that we keep in mind and why we settled on the particular one I'll introduce in a second, is we want it to be informative, right? So it should really be good in distinguishing different things. Then it should be interpretable. I mean, I want to be able to talk about it. That's what, if you talk about, there's a whole bunch of wavelet things that I personally find very hard to get used to. There's also some of the topological estimators that also really take a long time to build an intuition for what those different Betty numbers and such would tell you. So I think it should be interpretable and perhaps also relatively straightforward to learn, like get used to the statistics. Then predictable. So ideally you want a mathematical framework that for a cosmological thing, for Gaussian random fields, for, as things move, like that have an analytic way of predicting what I should find. That would be very nice. Should be robust. So if I just change a point, my statistics shouldn't change dramatically. So, for galaxy surveys, people think about, fiber collisions. I might not exactly get all the galaxies that are very close together. If I have a statistic that depends very sensitively on just the closest pairs that I have, that might not be so great. Then I think what I want is I want a minimal number of nuisance parameters. So I don't want to be, try out for this binning or that binning or like smooth on this scale and then smooth on that scale. Sort of ideally, it should just be, don't have too many parameters. So they don't have to, do too many checks. Then it necessarily needs to be fast to compute. That's a little bit sort of the downside, I think, of for decades people have been talking about doing third 3-point functions, 4-point functions, 5-point functions, but in reality they actually don't do it. The reason is because it's very slow to compute and it's really hard to deal with boundary effects. So, interestingly, the earliest of papers you read, right, if you go back and read Peebles in all the early catalogs, they already always talked about the third 3.4.5 point, and we're looking at the scaling relations. But then lately, that's actually not so common anymore. Anyhow, so it should be fast. I personally like it if it does no binning, no averaging, because I feel it retains all the information of the data, or a lot of the information in the data, if I don't do all this extra averaging. And then there's sort of a theoretical sense of it could be complete to some symmetries. So in this case that I'm going to have is like, it will, for any isotropic field, the set of statistics I'm describing is actually complete. Anyhow, you should be thinking about what's missing, what is, but anyhow, so this is the type of things that you then have in your mind to pick out of this infinitely large space of possible statistics you could make, to pick out some that you want to develop and then apply on your data and use it to interpret what you're measuring. And so here's just that first paper, is the archive number. I already uploaded the PDF of this talk I'm giving to the folder that's described at the very top of that page. So you can look it up, and if I'm going too fast or too slow, you can look things up already. And so what we do is what we call the nearest neighbor distributions, and we call KNN CDFs. The purpose of this slide is not for you to read all the math part. The only thing I want to try to relate is what we're measuring is the probability of finding k points inside a given volume. And this connects directly. So it's finding the probability of more than k, and 1 minus that will give you finding the probability of less than k in that volume. These are totally connected to the probability of finding exactly 3 points in a given volume. That's what you might know as counts in cells. That is a discrete distribution that if I throw down a random sphere of a certain volume, of how many times do I find 0, how many times do I find 1, how many times do I find 2 galaxies in it, that's a discrete probability distribution function. And these P of k's that appear in that sum, they all involve integrals over all higher order connected endpoint functions. So this is the 2-point function, the 3-point function, 4-point, all the way to infinity. So all of them actually contain a piece of each of the endpoint connected functions. So that's why this is a nice statistic to use if you are interested in beyond 2-point functions, because they do include all of them. So might as well measure these. So let me just walk you through how you go about it. Our red things here are just our galaxy positions, or the sample that we want to do. What we're going to do now is we throw down random points here in blue, and for those random points we go out and find the nearest data point. So this one here went out and found this is the nearest galaxy to this random point. Another random point here, that was the nearest one, and so on. So now I can throw down 1 trillion of those blue points, and so make 1 trillion measurements. And what I then do is I just sort the list of measurements I get from the smallest volume to the largest volume. And now I just divide by the total number of measurements I did. And now I have the fraction, which will go to 1, where I measure this volume or less. Right? So I get the cumulative distribution function of the volumes I measure. But it's a perfectly smooth function, and it's independent of how many galaxy points I have. If I only have 3 galaxies, I still have 1 trillion measurements and have a very funky shape, but it only has to do with exactly how those 3 points are aligned. But what that means for me is the nice thing, I always get to work on smooth functions. Right? So my statistic is perfectly smooth, and I'm not worried about sort of having the noise of having just a few points already be in the objects that I'm using. It'll become a property of this curve, but not, but I always get to work with curves. And that part's really nice. The only thing with CDFs is they always S-shape. And if you plot it on a linear scale, it's just really boring to look at. So the nicer way to look at is this one, where you go logarithmically on the y-axis. So this way you see the tail already on the left side. And then as it goes way up to 1, what you do is once you reach 0.5, you just plot 1 minus the CDF. And then you also get to see the tail on this side of how exactly it approaches 1. And we call that the peaked CDF, and it's a very nice way to visualize and really be careful about the tails. And so if I make 1 million measurements, this is exactly the number. It goes down to 10 to the minus 6. Right? So I can probe the tails very carefully with these statistics and then visualizing it like that. But again, to do this search to find the first nearest neighbor, you use a KD tree. It's built into your Python and Julia packages, MATLAB has one, Mathematica. Any tool you want to use will have a KD tree for you already, and it's n log n fast. So it's super fast to calculate these statistics. And then, yeah. And so then we have analytic predictions for this in the Poisson case. So here I'm plotting these peaked CDFs for a sample of 1 million points, Poisson points. The dashed lines is my analytic expectation. And you see the measurements are just, perfect. And the nifty thing now is having this probability of finding 3 or less points inside a volume. I can combine that with the probability of finding 2 points or less in that volume. If I subtract the 2, I find the probability of finding exactly 3 in this volume. Right? It was 3 or less, and I subtracted 2 or less, so what's remaining is just having exactly 3. So these, once I've measured these functions, I can subtract one of the other, and I immediately get these P of n, sort of the probability of finding exactly 0, finding exactly 1, finding exactly 2. These are these counts and cell distributions. So now one measurement gives me all these answers, the counts and cell for all possible volumes. And just to give you a sense, all the work up to now, including what's included in CoreFunc, which is a package everybody's using, when people wanted to measure this, what they did is they threw down 1 million random spheres, and then they counted. So for any volume they wanted to measure, each time they had to throw down 1 million or 10 million spheres, then do that counting. And that's why very few groups were wanted to use it, because it's just boring. I mean, and slow, and then you have that nuisance parameter. Okay, which one am I going to pick? We got rid of all of that, right? Just using that tree, you can now choose whatever scale you trust, maybe your analytic model that you want to model to. Anyhow, so that's very nice. It's just practical stuff. And then it has this nice property of what you would expect, that in the Poisson statistic, the only parameter you have is the mean density. And if I know the first nearest neighbor distribution, from that alone, I can predict all other nearest neighbor distributions. That's exactly for that reason. There's only one parameter that goes in. So give me one of those functions, I can get all the others. Now for a Gaussian, has 2 parameters. So if I know the first and the second, I can get you all the others. But I'm also fine with the third and the fourth to give you the others. So that's also a nice thing. And then I spell it out exactly, but essentially you just have the variance as a function of volume that you have to plug in. And so now for a typical cosmology situation where you have a linear Gaussian field, you can immediately predict exactly what you should find. If you have this many tracers and this sigma, you can predict the outcome of what you will find with these many tracers. And it has that nice property again. Yeah, just 2 of them are enough to specify the whole field. And this is sort of just visually what that looked like. This one is Poisson, so unclustered. Then you've got particles, your dark matter particles, the same mean density, a bit more clustered. Halos, more clustered, right? And so you get the sense, okay, the variance is bigger, right? And the peak shifts. So you're more, and so you can think of this, my typical voids are actually getting bigger. The probability that I have to go like 30 megaparsec, or that it can go 30 megaparsec and still have not found a particle, is bigger than it is for any of these other cases. All the other cases, if I go to 30 megaparsec, the probability is very low that I have a point in the volume that is the center of a sphere that is empty. Anyhow, yeah. And it's very robust. So this is a bit of a busy plot. But what we're doing is we're comparing 2-point function measurements with these cumulative distribution function measurements. And what we want to do is we want to see whether we can see a difference between something at redshift 0.5 and a sample at redshift 0. If we take the 10 to the 5 most massive halos in the same co-moving volume at redshift 0.5 versus redshift 0, they should have a slightly different clustering. A bunch of things happened. And what we do is we calculate the mean 2-point function over 1,000 different realizations. And then we just look at a single realization and say, compared to the mean, what is the 2-point function? And so that's the fiducial thing that we divide out in this line. And then for a single realization, we ask, okay, between redshift 0.5 and redshift 0, if I divide the two-point functions, I get this purple line. But when I plot the variation from realization to realization, that's just for 15, we plotted it as a dotted line, you see it's the same. So we just can't really tell, maybe we have this point here, but the spread between realizations is already as big as the measurement that we're trying to make. Whereas for the CDFs, you see the variation from realization to realization is much more sane. It's actually not as noisy. And the actual signal comparing redshift 0.5 and redshift 0 is dramatically, or it's much more obviously separated from sample variations. Yeah, and then you can turn that into corner plots and parameter inferences. And it's just long story short, what you would have anticipated anyhow is that you have a somewhat nonlinear field. So the 2-point function doesn't contain all the information. This statistic adds extra information. And so when we do that, and include it in these typical parameter constrained corner plots, you're just seeing that you gain by adding these statistics. And here we go, add first neighbor distribution is the orange one. The red, we use 2. If you use 3, if you use 4, you can see, okay, for this particular field, it's probably enough if you use 4 of those nearest neighbor distribution that captures most of the information you can get out of the isotropy. But this is always very specific of how non-Gaussian is it and what's the exact number density. But I think it just shows it's practical. I think what we then did in the second paper was to generalize this to situations where you want to cross-correlate. So, very often in astronomy you want to do that. You have a few high-energy neutrinos and you're curious, does this come from the large-scale structure? Does this correlate with the distribution of AGN? Is one example. You have many others. And I think this may very well be where this application, where this framework becomes even more useful, because what we're doing is we're actually testing something more than just whether there is a correlation, because Pearson correlation coefficient, it's all about whether there's a linear correlation between the two fields that you're looking at. This one actually tests about dependence. is there anything between these two fields where one could depend on the other? And so it's more general in that regard. So I don't want to go through all the math. All it's just saying in the uncorrelated case that the CDF we can measure, if it were uncorrelated, it would just be the multiplication of the probabilities we have from the two fields separately. But by now, essentially what we do is exactly the same procedure. Random point thrown down, you find the first nearest neighbor in the one data set, then you find the first neighbor in the other data set, and you take the maximum of the two. Take the one that's farthest away, and that's what you store as your CDF now. And while you're doing it, you already make the other two lists as well, so exactly the same going as what you did before. Now you have three lists at the end. One is the joint and the individual CDFs, and between the three, you can now subtract out that bit that you would have if it's uncorrelated, and the things that remain are this, I keep saying correlated, but I really mean statistical dependence. So here are these examples on Wikipedia where you have a zero correlation coefficient for this sample because it's just not a linear correlation. You know, X and Y are non-linearly dependent on each other, and the correlation coefficient would be zero. In our case, you would always have a signal for all of these. And yeah, so I think that'll be quite useful. And then we have a few more examples like this, and it has exactly the same properties, that the individual spreads are smaller, and the actual signal separates much more as compared to a two-point correlation analysis. Okay, so I'm going to skip a couple of those things. And so I have a chance to just perhaps show you a few applications of this. But a couple of the points I wanted to make is the predictability. I already showed you what we can do for the Gaussian linear case. It's really trivial. We can predict all the counts in cells. But there's all this work by Sandrine Codis and Cora Uleman, and there's, of course, decades of analytic work on this, where people have been thinking about how to predict the PDF of the cosmological density field. And if you have a theory that predicts the PDF at any smoothing scale, that's all we need. That as soon as you have that, you can immediately turn that into predicting the K and N distributions because of their connections, close connections with the counts in cells. Here's just, anyhow, so that's really nice. So we have analytic ways already of doing it, and then many numerical approaches that you might have of using Sildovich or 2LPT type predictions. All of that carries over. So that's nice. And I say this because a lot of other, we heard slime mold examples, or we hear about disperse or different topological things. There, in many of those very interesting statistics, we unfortunately do not have those, easy to understand analytical techniques. And so then, that's something nice about this one. And it's not that this is the very best statistics of all. It's just, this is super useful. It's really easy to do. And, that's the point I'm trying to make is, we might as well do this one. If we have another statistic that also has extra information, great, let's include that one too. But yeah. Okay. Yeah, and then, if we have even when we just do spherical collapse modeling, we get really good results from 15 megaparsecs up, and that's really quite a bit better than many very fancy, complicated-looking theories that people will promote. I showed that one already. Okay, so now lots of applications. One really quick thing we did with Liam and Garrison and Dan Eisenstein was just to use that to look at their self-similar M-body simulations, get a little bit of sense of how, of what converges when. And I think, if you're into some of the numerical convergence things, I urge you to have a quick look. It's quite interesting that the density field can, in fact, converge at relatively small particle numbers. Then we did an application that's really relevant for the galaxy formation. For for the large group of people that are excited about DESI and the type of new data we're having to get cosmological parameter constraints. We showed that this particular second-order Lagrangian bias expansion that a number of groups now have been excited about as a sort of a unified framework to describe the galaxy biasing that you have to model in your observed data to back out cosmological parameters. And we showed that it actually very nicely plays with these K and N, and that it's complementary to the two-point analysis. Oh, I see. All right. I was having too much fun. Oh, okay. We have a cool application on modified gravity models where it sticks out like very strongly in this. And then there's an application of actual data on looking at the clustering of the 1,000 richest red mapper clusters from the SDSS, where we've now worked through a whole bunch of these issues of window functions and selection bits. And so I'll just skip some of the parts, just leave you the conclusion. Like all I want to get across is like there's a, in some sense this is really simple. It's just the nearest neighbor density estimator. The key point is what you want to do is you want to do it for all k, and then you have a whole sense of how you analytically connect to the way you think about cosmological density fields. It's super fast, and you will find on some of those slides I give a link to a GitHub repository where there's example code where you can try it out. All I want to say, it's sort of useful, and I think there is many applications where this will be useful, not just the particular one I introduced it for, because we just have so many examples of discrete data in astronomy. And the paper we're about to finish soon is the generalization to do discrete and a continuous field. So the one I showed at the beginning was one discrete field, then a discrete and another discrete field. And the one we're doing now is a discrete and a continuous field, so galaxies and reglensing maps or like those types of things. And that should then pretty much cover many of the situations you'll find yourself in. Thanks so much for paying attention. Thanks.
Questions for Tom? Yeah.
Great stuff, Tom. One quick question. Redshift space distortions, right? So all of this is great in 3D isotropic space. One advantage you might argue for the correlation function is we have this machinery to go to a projective correlation function to get rid of that annoying redshift space distortion stuff. Is there a way, have you thought about something smart to avoid having to sort of forward model redshift space distortions in this approach?
Yeah, we've done 3 things so far in that one. None of them published. One where we sort of thought about a cone and sort of a, funny shape around it. You look at the 45 degrees forward and 45 degrees backwards, and then the ring around it. Sort of separating out. You still do the same nearest neighbor thing, but then you look in the bin of in which of those structures it's in. That we didn't find very good, and I think it's to do with these sharp edges, that there's some extra ringing, that the whole thing wasn't so great. A second thing we've done in the context of seeing how well this works for AP test, Alcock-Paczynski test, is by actually stretching the whole data in a volume preserving way. Then you do multiple measurements, but few times you just keep stretching your data. That's a bit nicer actually. It's closer of doing ellipsoidal searches. And there's a third one now where we're really looking more at cylinders, sort of cylindrical coordinates rather than the spherical one, sort of splitting it in the delta C and radial direction, much closer to what we do in the two-point function. And that currently looks very promising. I mean, that indeed, it's probably because of the intermediate scales where the usual Kaiser, yep. And that, we have one plot and looked too good. So anyhow, I have to wait for Sandy to come back from vacation to double check.
Questions? Yes.
I have two questions. The first is the KNN CDF statistics does it depend on the resolution in simulations? I can imagine if you have more particles or less particles, the location of the peak will change, right? Can you fix that?
Yeah, absolutely. And so, right, it really depends on the density of the tracers of what exactly you're going to measure. Now, sometimes, you know, if I want to study only really large-scale, distribution, what I do is I just downsample my data set until I have the mean density that I want to be studying. But now, say I downsampled it by a factor of 100. Well, now I have 100 realizations of this downsampled field. And so, in fact, I do exactly the same measurements and then concatenate it in the list at the very end and still just do one single sort. And now I'm focusing more on the larger scales. So if you look at the very last appendix of our first paper, we describe
I see.
how that goes.
And the second question is related to the difference between redshift 0 and 0.5. You showed that the correlation function looks similar while these statistics are different. I'm wondering the difference comes from the growth of void? Because the peak looks located at a very large scale. And
yeah, that's a good, let's see, where was it? So that's likely a good hypothesis.
yeah, the 2-point correlation functions look similar. That you say the smaller scales higher scales are roughly the same.
Yeah, although the CDF actually in the small scales here, that we divide by is a little bit bigger. So it looks like on small scales,
Small scale.
you were a little bit denser.
Yeah.
Just the growth of structure. You did get somewhat denser
Yeah, I
on
see.
small scales.
Yeah.
And then that's what led more to that
Okay.
difference. But you have to look, it's always so crazy because it's such small fractional things. On the other hand, you have so many measurements that small fraction is actually trivially well measured.
Okay, we have time for one quick last question.
Do you have a sense of why that doesn't get reflected in the one halo term of the 2-point correlation function?
It's just noisy at this particular number density. And it's also this particular way of how we are selecting, right? We're picking the 10 to the 5 most massive things at redshift 0.5 and the 10 to the 5 most massive things at redshift 0. Which, I mean, whatever we do, I think we've just done a bunch of different bits, and it's just every time true, though, that the noise is just stronger on this density squared statistic. I mean, also not too surprising, right? If you think, because for the 2-point function, it's always, you already have to be on a galaxy to begin with. And so I don't find this too surprising. It's more noisy.
Okay, so let's thank Tom again. Thank you very much.
Thank you.
So it's coffee break time, so we'll be back in 25 minutes.